All right, so this video is going to explain why the 4n plus 2 pi electron rule is used to assess whether or not something is aromatic, okay? Huckel's rule, right? So we use the MO diagrams to kind of explain that. And so remember from general chemistry, MO diagram for O2, or even my previous videos, I've drawn this out for you just to explain how we can bring two atomic oxygen atoms together to make one O2 molecule. And that gives you a molecular orbital diagram, or MO diagram, right? Now, starting from the bottom, we have a sigma orbital, and then we have a sigma with an asterisk, okay? So that's a sigma star. And then we go sigma, and then we have two pi orbitals that are equal in energy. Those are called degenerate orbitals because they're equal in energy. And then we have two pi star orbitals that are degenerate. And then at the very tippity top, we have a sigma star orbital. Okay, so that's basically, how the molecular orbital diagram is laid out for oxygen specifically, right? And so the point that we want to kind of hammer in there is that when you have, if you look at the bottom, you have two s orbitals in the atomic oxygens. If you combine two atomic orbitals, you're going to get two molecular orbitals out, okay? And one's going to be low in energy, one's going to be high in energy. And the low energy one is the bonding orbital, and the higher energy one is the antibonding orbital. So that's what sigma star represents, or pi star. Those are the antibonding orbitals, okay? And I'll remind you what that looks like in terms of orbital, like p orbitals and stuff, shortly. But it's basically when the phases don't match up, okay? But, in addition to that, we have our molecular orbitals laid out, and when we're filling up the electrons from each oxygen atom, the valence electrons it contributes, there's 12 total, and we still want to follow the rules for building up and filling those orbitals. So we start with the bottom, and then once that's filled, you go up to the top. And notice at the very tippity top in the pi star orbitals, there's two unpaired electrons. So we don't pair those up because they're degenerate pi star orbitals. And so what we want to do is, or the important thing to grasp from this is that we have oxygen having two unpaired electrons, and it acts like a diradical, right? And so we brought this up in the radical chapter when we mentioned how oxygen can react with double bonds in like oils and stuff like that. And so that's how they spoil. They get oxidized by elemental oxygen because it reacts like a diradical, forming peroxides and stuff like that. Okay, so these pi orbitals, these top four orbitals, are the orbitals of interest when we're talking about the 4n plus 2 rule. And these are what's going to help us explain the stability of aromatic species, because it just comes down to the pi orbitals and the pi bonds in those species, okay? And I also want to point out and remind you that had we not drawn the molecular orbital diagram for elemental oxygen, we wouldn't be able to explain the fact that it can hover in between two magnets, right? So if we have liquid oxygen, it'll just hover in between two magnets because it's paramagnetic, okay? And that's explained by these two unpaired electrons in the molecular orbital. Okay, so let's take a look at these bonding and antibonding orbitals. So we've got, I'm going to color these in red and blue just to show you or point out and emphasize the fact that the top orbitals, those are bonding pi orbitals. That's a pi bond, and that's when the red and the blue match up, okay? That's when they are in phase with one another, okay? Now, notice the lower orbitals, the blue and the red, are opposite of one another. So they repel one another, and so they end up with that dotted line in the middle. That's called a node. So they're like repelling one another, and that's why they're called antibonding orbitals, okay? Now we can draw almost like a molecular orbital diagram for just a pi orbital. So if we have two p orbitals, remember we have to have two molecular orbitals coming out, right? So we have two p orbitals going in, we have one pi bonding orbital and one pi antibonding orbital. Okay, so the bottom one would be when they're in phase with one another, because that's lower in energy, they're bonding. And then the top one would be when they're out of phase, and that's the antibonding orbital, indicated by a pi star. Okay, and again, that node is important. Okay, so now we have one electron in each of those p orbitals, so we have 2 electrons in the pi bonding orbital, and then nothing in the pi star orbital. Okay, so again, just want to remind you, if we have n number of atomic orbitals, when we combine those to make a molecular orbital, we still that results in n number of molecular orbitals. We'll just have an equal number of bonding orbitals and antibonding orbitals. You can see here we have 8 total atomic orbitals, and then 2, 4, 6, 8 atomic orbitals as well. And notice each bonding orbital has a respective antibonding orbital. Okay. Okay, again, so just focusing on the pi and the pi star, let's take a look at benzene's molecular orbitals. All right, so let me just draw out benzene again, and then we'll draw some p orbitals sticking up and down. These ones I'm drawing all in phase, right? So I have the blue down and the red up. That means they're all in phase. What you can see is that we have 6 p orbitals total, right? So that means that when we draw the pi bonds associated with this, we can have 6 molecular orbitals corresponding to these 6 p orbitals, okay? And I went ahead and cheated and I drew all this because you don't want to see me struggle, and now it looks gorgeous. So we have those 6 p orbitals creating 6 molecular orbitals. The bottom is psi 1, and then we have psi 2, psi 3, degenerate bonding orbitals, and then we have psi 4 and 5. Those are degenerate pi star, or antibonding orbitals, and then we have psi 6 on the top. That's the an antibonding orbital as well. Okay, so the bonding orbitals are going to be the bottom orbitals. Okay, so notice the dotted line that's equal in energy to the p orbitals, the atomic orbitals. That is like the barrier. So like the bottom is bonding, the top is antibonding, okay? And of course, psi 1 again is the most stable bonding orbital, okay? Psi 2 and psi 3, these are, since they are occupied by electrons in this case, they are also the highest occupied molecular orbitals. They are abbreviated as HOMO, so that means the highest occupied molecular orbitals. This is where the chemistry occurs, right? Because you have electrons at the highest energy level, and then typically the HOMO reacts with the LUMO, or the lowest unoccupied molecular orbital molecular orbitals. Okay, and those would be psi 4 and 5, the antibonding orbitals. Okay. Now, notice that all of the bonding orbitals in this particular molecular orbital diagram, they are occupied, okay? Now, this is one of the criteria for aromatic compounds. If all of the bonding orbitals are occupied, but also none of the antibonding or the non-bonding orbitals are occupied, okay? So I haven't drawn you the non-bonding orbitals yet. I'll show you that in a second, but, sorry. Getting willy-nilly over here. And non-bonding basically lie on that dotted line, okay? But again, the criteria for this is as long as we have all of our bonding orbitals occupied and nothing else, then we're good to go. And it does at least meet the 4n+2 criteria, okay? It does still have to be cyclic and planar, right? And cyclic, planar, and conjugated, sorry. And so that might seem a little weird at first, but let me explain to you how you can draw those diagrams, and that's using something called frost circles, okay? So let's say we have I'm trying to draw a square right now, and my iPad wants me to draw a rectangle, so I'll draw this poopy square. Cyclobutadiene. And then we have cyclooctatetraene, okay? It's like a stop sign, right, with 4 bonds, or 4 pi bonds. So if we recall the cyclobutadiene was anti-aromatic, and we did say that cyclooctatetraene was non-aromatic because it wasn't planar, right? So let's say if it were planar, this would also be anti-aromatic, okay? Because it's cyclic, it's conjugated, and if it were planar, it would have 8 pi electrons, which is the 4n electrons, right? And so that would be technically anti-aromatic. Remember also that anti-aromatic species are very unstable. So for example, this cyclobutadiene, if you react it with itself, well, first of all, you can react it with itself. So there you go. That's kind of comments on its instability, and it does some cool stuff actually. So it will do a cyclic reaction with itself to make this 3 like ring species, and then it reacts again, shifting those sigma bonds around, and think about what that forms. It forms cyclooctatetraene. That's fancy, right? So the point here is that anti-aromatic species are very unstable, and they do what they can to achieve stability. And in this case, it forms cyclooctatetraene, but the one that is not planar. Okay, that's the actual reaction. Okay, so the reason why I brought up the fact that cyclooctatetraene would be anti-aromatic if it were planar is because I wanna touch up on that and explain why using frost circles. Okay, so this is also known as an inscribed polygon method. And basically what we want to do is draw the ring in question and then draw a circle around that ring. And that circle needs to touch every point on that ring. Okay, almost like a tangent line, right? And then what you do is you draw a dotted line going through the center of that ring in the horizontal plane. Okay, and now what we've done is we've created basically the order of the orbitals, molecular orbitals, from bottom to top. And for example, the bottom point, there, one second. Here we go. So that bottom point would be 1 orbital, and then and then you get 2 degenerate orbitals, then 2 degenerate orbitals, and then they top highest energy orbital. So it looks like that on the right. Now, this is done. It is a nice method to write out the molecular orbitals of various rings if you're trying to determine if the compound is aromatic, right? So remember, if all the bonding MOs are occupied and nothing else is occupied, like the antibonding orbitals, then it's aromatic. And so again, that dotted line is the kind of the point that divides the antibonding and the bonding orbitals. And again, the dotted line also, if the orbitals lie on that dotted line, then they are non-bonding orbitals, which is also bad to have electrons in. Okay, so what I want to do is draw out a bunch of these frost circles for you with varying size rings. And the reason why I want to do this is so that, because everybody's going to draw their rings differently, right? But if you draw it one way or another, you could have the orbitals lie above that dotted line, or when they're actually supposed to be below that dotted line. So I'm basically giving you this as a guideline. Okay. Another thing I want to point out is we don't draw benzene sideways like this, right? So if we drew it that way, we would have 2, 2, and 2, and then the dotted line would have 2 orbitals on it. But we have that lower energy orbital. And the reason for that is because if we draw all of that represents the bonding orbital, where all of the p orbitals in benzene are lined up in the same phase, okay? And there can only be one occurrence of that, and so that's why that's the lowest bonding molecular orbital, and that's why we also draw the frost circle with a point of that ring on the very bottom, because there has to be the lowest energy bonding orbital, okay? And that's the one where all of them are in phase. So here's the cyclobutadiene frost circle. We can see we have 1 antibonding orbital on the top, and then we have 1 bonding orbital on the bottom. And then we also have two non-bonding orbitals along that dotted line. Okay. So remember, cyclobutadiene has 2 pi electrons. So that's 4 electrons total. If we fill it up, that means we're going to get 2 electrons in the bonding orbital on the bottom. Awesome. But we're also going to get 2 electrons in the non-bonding orbital. Remember, oxygen had 2 unpaired electrons and it was a diradical. It's the same thing for cyclobutadiene. It is a diradical, and that explains why it's super reactive as an anti-aromatic species, and it undergoes that cyclic reaction with itself, right? Super reactive, and then you get 2 rings put together to make the 3-ring system, and then it rearranges again to make the cyclooctatetraene. Okay, so again, this is an explanation as to why anti-aromatic compounds are very reactive and not super stable. We can draw another example of this in a little bit, but what I want to do is draw, like I said, a bunch of those frost circles with the different size rings. So we'll do 4, 5, 6, 7, 8, 9, and this will allow you to see that, for example, in this cyclopentane or cyclopentadiene or whatever kind of 5-membered ring we're dealing with, we should have, if we're drawing the ring properly and bisecting the circle properly, we should have 3 bonding orbitals on the bottom and then 2 antibonding orbitals on the top. Okay. Now I imagine if you drew the 5-membered ring, you can imagine if we drew this 5-membered ring improperly, we could have those 2 degenerate bonding orbitals. They could be up a little bit higher and almost on that dotted line, but we don't want them there. That's not the right molecular orbital diagram for a 5-membered ring. Okay, so I'm drawing you these so that you have them to reference. So keep them close. Okay, so we do have those 2 anti-bonding orbitals on the top and then 3 bonding orbitals on the bottom. Okay. And then we also have here, there's no non-bonding orbitals, and so we don't have to worry about that because the dotted line doesn't have anything on it. And that's going to be the case for a lot of rings. Not every ring is going to have them there, okay? So just keep that in mind. So let me draw, sorry, my iPad likes to do whatever it wants sometimes. I have a 5-membered ring. Let's go with this one. And let's say we had 2 pi bonds, and then let's say, do we do positive or negative charge? Yeah, any hands? No? Okay, I'll do a negative charge then. We'll throw 2 electrons there on that carbon, giving it a negative charge, which means we have 6 pi electrons to work with. Now what we want to do is fill up those orbitals, following the Hund's rule, the Aufbau principle, right? The building up. And so we have 6 electrons occupying all 3 of those bonding orbitals. And so since it's completely full, that's why this compound is considered aromatic, and it's also very stable. All the bonding orbitals are full, so it's like hella strong, right? Makes sense, right? Right. Okay. So again, all the bonding orbitals are full, nothing else is full, so it's aromatic. Okay, so I'm gonna copy and paste this because I'm gonna cheat, because it's, as you saw, it's kind of difficult to draw sometimes. And so what I'm going to do is give you another example, with a positive charge. Okay, so we know that the positive charge, no bueno, right? So that's 4 electrons total. That puts 2 unpaired electrons in the higher energy, in the HOMO, the highest occupied molecular orbitals. And so since there's only 4 electrons occupying those bonding orbitals, they're not completely full, and they're unpaired, so it's like a diradical, right? So this is anti-aromatic as well, because by definition it has the 4n pi electrons, and so they're using molecular orbital theory, we explain why it's so unstable, because it's got unpaired electrons. Fancy, right? I like it. I love it. I want some more of it. I'll try to draw another ring like this. Oh, that's just ugly, right? Now this is me making the point. Okay, do. So if I draw it kind of like not proportional, that dotted line is supposed to be the divider between bonding and antibonding, right? Well, the way I drew it, it only puts one bonding orbital and then 4 antibonding orbitals. But that's not the case. That's not the correct way to do this. And so that's why, again, I'm pointing it out to you, right? I straight up labeled the 4 and the 5 membered rings for you. And blam! Look at that. Check it out. Gorgeous. You know how long it took me to draw that 7 membered ring? Like, for real, though? The 4 membered ring. Boom. We got 4 electrons. That explains why it's anti-aromatic, right? The 5 membered ring with the negative charge. We got 6 electrons in the all completely filling the bonding orbitals. That's why it's aromatic. 6 membered ring for benzene. 6 electrons. 7 membered ring. 6 electrons. We want to fill it. 6 electrons for the 8 membered ring and 10 for the 9 membered ring are what we want in order to fill up these molecular orbitals, right? And notice for the 8 membered ring we have non-bonding electrons. Nice, right? So make note of all of these guys, right? Because you really want to kind of just have these as a quick reference so you can look at how many pi electrons you have and then how many are required to fill up all the bonding orbitals, and then you can determine if it's aromatic or not, right? So the 4n plus 2. The lowest energy orbital is one of a kind. Okay, so everything else has a degenerate orbitals, right? So you have the 2 orbitals that are equal in energy as you go all up, and then sometimes you reach the top and it splits up to 1 again, but sometimes it doesn't. The point is the lower energy orbitals are one of a kind. And look at the cyclooctatetraene and the frost circle. If we have 8 pi electrons, you can see that there's 2 unpaired electrons in the non-bonding orbitals, and that makes it a diradical, right? And it's anti-aromatic, but that's if it's planar, right? So remember, cyclooctatetraene is not planar. It has like a little ring puckering that forces it into like almost like a little chair, right? Or a little seat, I should say, because it doesn't look like the chairs for the cyclohexanes, right? So it's not planar anymore, and it would rather be not planar and non-aromatic than it would be anti-aromatic. That's because the molecular orbital diagram now looks different, and it's not a diradical anymore. Okay, so those are isolated alkenes now. They're not conjugated because those p orbitals don't overlap. Okay, and that's why the cyclobutadiene reacts with itself to form the more stable non-aromatic cyclooctatetraene. Okay, so remember that. You need to be able to explain that. Like, what's a good explanation for the cyclooctatetraene not being planar and preferring to be non-planar, okay, and undergo that ring puckering. All right, so these structures that I'm going to draw, are they anti-aromatic, aromatic, or non-aromatic? Okay. Now let's see if I can. Nope. Boom. What's up? Drew a little 1, 2, 3, 4, 5, 6, 7, 8, 9 membered ring there for you. Also, my wife thought that the far left anion kind of looked like a monkey face with some like tribal tattoo on his forehead. So that's why there's a monkey there now. Anyway, you can see that this particular compound is anti-aromatic because we have 2 electrons in the antibonding region. And yeah, the bottom, and it follows that 4n pi electrons formula, right? 4n plus 2 for the cation, though, cyclopropylium ion. And then this 9 membered ring right here, I'm not even going to try and draw that again. I actually just copy and pasted it from above, where it took me a hot minute to draw that. I'm not going to lie, I'm proud of it. Definitely draw that dotted line across, right? Sure. We have 10 electrons, right? 2, 4, 6, 8, 10. Yeah, it's supposed to look like that. So we have 5 bonding electrons, like I said. Refer to that chart if you want. And then That means we have 5 bonding electrons, 10 electrons occupy that. We have 10 electrons in conjugation, and so that is an aromatic compound. Okay, so again, draw your frost circle, point at the bottom, make sure you know how many molecular orbitals there are on the top and the bottom of that bisecting dotted line, and then or you can just know how many are bonding orbitals, and then you know that you need 2 for each of those bonding orbitals. So in this case it was 5 bonding orbitals, so we needed 10 to fill that up. If we have 10, then it's aromatic. Okay, provided it is cyclic, it also has to be planar, and it also has to be conjugated. But usually by the time we get to the frost circles, we're either assuming all that's the case, or we figured it out by then. Okay, but this is more or less just an explanation as to why something is aromatic. All the bonding orbitals are full, and that makes things super happy and strong. Or anti-aromatic, there's 2 unpaired electrons and it's pissed and it wants to pair those up and react super fast, like that cyclobutadiene. Okay, and that's all she wrote. You like it? Hopefully. Bye. Okay, bye.